All right. Well, I guess we stopped in the middle of a question this time. Not the brightest thing, but I never promised to always make sense. Anyway, we're rolling a single die. It's got 6 possible outcomes, one for each side: a 1, a 2, a 3, a 4, a 5, and a 6. And we did some theoretical probability. Now we're having, if the die is rolled 300 times, how many times would you predict or expect, I guess is another name word that works there, a roll of 1 or a 6? Well, let's first find the probability of getting a 1 or a 6. So the probability of 1 or 6 is 2 outcomes out of the 6 possible, or 1 out of 3. Then if we're asking how many times we predict something to happen or expect it to happen, that's expected value. So the expected value is always the probability of it happening times the number of attempts you make, the number of times you try. So in this case, the probability of a 1 or a 6, we said, was 1/3. And we're going to do it 300 times. So 1/3 times 300 is 100. So therefore, you would expect to roll a 1 or a 6 100 times if this was a fair die and everything was equal. Now, things aren't always perfect. That's theoretical probability. What happens in theory? Well, Johnny wasn't sure, so he rolled this die 1,500 times and got these results. So a 1 came up 230 times, 245 times he got a 2, 300 times he got a 3, 280 times a 4, 215 times a 5, and 230 times a 6. So each one is a 1 in 6 chance. So the number we would expect to get if this was a fair die, a die that was perfectly balanced, we'd expect them all to show up about 250 times each. So we see 3s and 4s have shown up a lot more than they should, and everything else has shown up less. So let's do the experimental probability of getting a 4. So the probability of getting a 4 is the number of ways you get a 4. So we got it 280 times, divided by the total number, 1,500 times. Even though this is experimental probability now, it uses the same equation. The number of times you get what you want, what you're looking for, divided by the total. It's the exact same for experimental and theoretical. So let's see on our calculator. 280 divided by 1,500. Ooh, that's not a very nice number. So let's go lowest terms if we can. I can divide them both by 10 because they ends in 0, so that's 28 over 150. I can divide them both by 2 because they're even. That's 14 over 75. I don't think we're getting any lower terms than that. And if it does say as a fraction, we do expect lowest terms, right? And then we can go to a percentage. So I'll do 14 divided by 75 to get the decimal and multiply by 100 to get the percent. And it looks like it's about 18.7% of the time. And we would expect it's only like a sixth, 16.6. So yeah, way above what it should be. New question. A card selected from a deck. So a deck of cards has 52 cards. So this has 13 hearts, 13 diamonds, 13 clubs, and 13 spades. These 26 are red. These 26 are black. And in every single suit, we have the number 1 to 10, plus a jack, a queen, and a king. And of course, the 1 is an ace. So there's 13 in each one. So we have an experimental probability we drew a card 50 times and we got 32 red cards. But this is asking, what's the probability of drawing a black card experimentally? Well, we don't have anything about the black cards. So this is an example of having to use the idea that if we know the probability of one thing happening and there's only two possibilities, we can use the complement, the opposite of that. So if we got this, we can find the probability of getting a red was 32 out of 50, which is 16 out of 25. 16 divided by 25 times 100, and we get 64%. Oh, of course. Well then, the complement, the probability of getting a black card is just 100% minus the probability of getting a red, because it's either red or black. It has to be one or the other. So if you're getting a red 64% of the time, well, that means you must be getting a black card 36% of the time, because they're the only possibilities. So if there's only two outcomes, this is called the complement. Now it's saying, what's the theoretical? So that was experimental, based on the actual experiment done above. Now we are looking at theoretical. What should the probability have been? Well, the probability of getting a black card, there's lots of ways to think about it. There are 26 black cards out of the 52. And that's the same as 1/2, which kind of makes sense, right? There's half the deck is red and half the deck is black, so it should be a half, or 50%. You also could have done 2 of the suits are red divided by 4 total suits, which is a half, and that would give you the exact same answer. And then why are these answers not the same? Well, I'm not going to write it out, but essentially, theoretical is what should happen in a perfect universe where everything happens exactly according to the math. But that's not how things actually happen in reality. You know, you can flip a coin and get 5 heads in a row. So the big idea is randomness. That's a terrible R. Randomness is a thing. So even though we know what should happen on average, theoretically, in any individual experiment, randomness can have it be quite different. Moving on, a pizza place has a 1-topping pizza deal where you can choose one of the following options. So you've got 3 options for the dough, then you've got 2 options for the sauce, and 2 options for the topping that you want. This is a great situation that we can represent by a tree diagram. So tree diagram, remember we start with a single point, right? And then we're going to have sort of option 1, option 2, and option 3 to fill out our tree. So in this case, option 1, we have whole wheat or gluten-free or regular. So those are the 3 possible outcomes at that first level. This is like our dough level. Now that we've picked our dough, now we'll pick our sauce. So if I went whole wheat dough, I can either get tomato sauce or Alfredo sauce. Same with if I pick gluten-free, I still have the option of tomato sauce or Alfredo sauce. And if I picked regular dough, I still have the option of tomato sauce or Alfredo sauce. And then finally, our third one is our topping, meat in this case. So you can go pepperoni or bacon, pepperoni or bacon, pepperoni or bacon. Trees are annoying. Pepperoni or bacon, pepperoni or bacon, pepperoni, or bacon. And each of these represents a single way through. This is the one where we got whole wheat crust and tomato sauce and bacon, for example. Let's do another way. So that's one possible outcome. Or there's the outcome where I got a regular crust with tomato sauce and pepperoni. That's another one. And in total, we have 1, 2, 3, 4. You just count the bottom leaves. 5, 6, 7, 8, 9, 10, 11, 12 possible outcomes. That's all it takes. What's the probability that a random customer comes in and orders a pizza with pepperoni and tomato sauce? All right. Now, in reality, you're probably not going to sell the exact same number. I don't think you're going to get the same number of like gluten-free Alfredo sauce pizzas as you do regular tomato sauce pizzas. But in this case, we're assuming everything's equally likely. So we're just going to count up how many there are and divide by the total number of outcomes, which is 12. So the probability of, we want tomato sauce and pepperoni. So there's a tomato sauce and pepperoni, there's a tomato sauce and pepperoni, and there's a tomato sauce and pepperoni. So there are 3 branches that have tomato sauce and pepperoni. We don't care what the crust, the dough is, because it didn't say anything about that. And there's 12 total options, so this would be 1 out of 4, or 25%. What's the probability that someone will not get a gluten-free pizza? Well, we go back up to the table again, and we find all the branches that don't have a gluten-free pizza. Let's go that one. So these ones in the middle all are. So these are not gluten-free, and these are not gluten-free. So I've got 8 of them. So the probability of not gluten-free is 8 out of 12, or 4 out of 6, which is 66.7%. Or you could have done the probability of not getting gluten-free is 1 minus the probability of getting gluten-free, and using that that trick we used earlier when there's only 2 options. So it would be 1 minus 2 out of 6, or I guess it was 4 out of 12, wasn't it? There were 4 ways to get gluten-free, and then that would give us 8 out of 12, which would give us the 66.7%. Again, same idea. So that is it for these 2. There's only 2 pages left, so 1 video, and then we're done.